Hi everybody, this is your lecture 6 and we're going to see normal distribution in this week. So by the end of this week, you should be able to identify a normal distribution. You should be able to state the properties of a normal distribution. You should be able to locate and find the area under a normal distribution. Okay, so let's start with the sample from a population. Okay, so we know that a sample is a part of the population which has been chosen randomly to participate in a study. Yeah, and a sample is most likely to represent the population in all its characteristics. Remember, we have seen in week 1, what are the characteristics? They are the summary statistics. Yeah, the summary statistics helps us to identify where the data is located, that is measures of location, and how the data is spread, that is how the data value is distributed, and that is measure of spread. Okay, so we know the different measures of locations and different measures of spread. We are going to use mean to describe where the data is located. Yeah, that is a position. And we are going to use standard deviation to describe the spread of the distribution. Okay, so these characteristics of the sample are used to make generalization about the population. So we're going to make a transition from sample to population. Okay. So for sample, we have seen how to determine or estimate the sample mean to describe the measures of location. And we know how to determine or estimate the standard deviation to describe the spread of the data. So we know how to use statistics to describe the data from a sample. Similarly, to describe the data from a population, we have something called parameters. So parameters helps us to describe the data from a population. Just like the mean for the sample and the standard deviation for the sample, we have similar characteristics for the population. And for the population mean is denoted by mu, which will help us describe the position of the distribution. And the population standard deviation is denoted by sigma, which will help us to study the spread of the population distribution. Okay, so now that you know the difference between statistics, the characteristics for the sample, and the parameter, the characteristics for the population, we will go back to week 2, where we have seen that when we have a sample of continuous quantitative data values, we can represent it graphically using a histogram. Yeah, so if we have a raw data, we can represent it using a group frequency table and summarize the data using a histogram. Yeah. Now, we also saw that while we can summarize a set of data using histogram, these histogram can also help us to show the shape of the data. Yeah. And we have seen that when we have data spread towards the left of the histogram, the shape, it's called negatively skewed. And when we have the data spread towards the right, we call it positively skewed. And we have a data symmetrically spread about the mean, we call it symmetrical data. Yes. So we have seen 3 different types of data. Now this is for the sample. Now if we have n number of samples or a large number of samples, we are talking about a population. Yeah. When the sample size is really large, we're talking about a population. Yeah. So we're going to make a transition from sample to population. The population to which such a sample belongs is said to have a normal distribution. So a normal distribution is a symmetrical distribution, because here we are talking about a large number of samples, or a sample with a large size. Yeah. So the population distribution will have a symmetrical distribution. Yeah. That's how it looks. Yes. We'll have a symmetric distribution, and such a distribution is called normal distribution. Yeah. So this density curve, or this population distribution, or this probability distribution has the shape of a bell. It looks like a bell. Yeah. So sometimes it's also called a bell curve. It is sometimes also called a Gaussian distribution. So some textbooks call it Gaussian distribution, population distribution, probability distribution, density curve, or a bell curve. Okay, so we have seen this example previously. Yeah, histogram of a sample of students in a class with height. Yeah, so for a sample, we can determine the mean and the standard deviation S. Yes, now if we collect the height of students from the whole population, the distribution will look like this, which is symmetrical about the mean. Yeah, approximately symmetrical about the mean. Yeah, for a population. Yes. And this distribution, this sample has the same general shape as the population, but the population distribution is smooth. Yeah. And for the population, the mean is fixed, mu, and is represented by mu, and the standard deviation is also fixed and is represented by sigma. Okay, so what we see from this distribution is this distribution is symmetrically distributed about the population mean. That is, 50% of the population will have a height below the population mean, and 50% of the students will have a height above the population mean. It is very important you understand that. 50% of the population will have a height below the population mean. 50% of the population will have a height above the population mean. Okay. Okay. So now we can see such normal distribution around us. Okay, because we are talking about a population now. Okay. So there are many types of data which can be considered to have population with a normal distribution, like the cholesterol. Yeah, we saw the example of a sample, but if we take all the adults, for example, in UK, for the population, the distribution will be smooth and symmetrical. Approximately, sometimes it is approximately symmetrical. Yeah, and that distribution is called normal distribution or a bell curve. Yeah. So we have other continuous data because they are in the continuous scale. Yeah. So we have other continuous data like blood pressure, height, IQ level, weight, which also the pop will have the same symmetrical distribution called normal distribution for the population. Okay. Yeah. And the distribution is symmetrical about the center, that is the mean. Okay. Now let's take the cholesterol example. Okay. So consider that the population mean is 5. That means, let's consider that the population mean is 5 units for the cholesterol example. Yeah. So this means that 50% of the adults, 50% of the adults will have a cholesterol level less than 5 units, and 50% of the adults in the population will have a cholesterol level above 5 units. So 50% will have below 5 units, 50% will have above 5 units. Okay, I'm talking about the population now. Okay, that means so this is your mean, population mean. As you go away from the population mean, either side of the mean, it is less likely to occur. Yeah, it is less likely to find an adult with that cholesterol level. Okay, so that means what I'm trying to say is, as you go towards the extreme end of the population mean on either side, the adult with that cholesterol level around this region is less likely to occur. And this will be our outliers. Okay, so that will be our outliers. So for a normal distribution, the location is specified by the mean, okay, and the standard deviation will help us to determine the spread. So here the standard deviation is 5.5 minus 5 is 0.5. Yeah? So the spread is specified by the standard deviation and the location is specified by the population mean. Okay, so let me make it clearer. This will make you understand that more clearer. Okay, so the population mean mu, if I increase this value, if I increase the population mean, what will happen to the distribution? That is, if I increase the value, for example, if this was 5 units, and if I increase to mu is equal to 6, what will happen? The whole distribution will shift towards the right. The whole distribution will shift towards the right, isn't it? Similarly, if I decrease the population mean, so if I increase the population mean, the whole distribution will distribute towards the right. And if I decrease the population mean, that is from 5 to, let's say, I decrease the population mean to 2, then the whole distribution will move towards the left, isn't it? Oops. Okay, L2 move towards the left. So what's happening? When you change the mean, the distribution moves towards the right or towards the left. So the population mean will help us describe the position of the distribution or position of the data. And similarly, the population standard deviation will help us determine the spread of the distribution. Let me take an example here again. So if I have a distribution of this style, and now if I increase the standard deviation, the spread is going to spread out more because the standard deviation has increased. We have seen an example. We have seen many examples in the last couple of weeks. So when you increase the standard deviation value, the spread will increase. And you also see that the curve becomes flatter. So that is the height decreases. Height decreases and the width decreases. Width increases, sorry, yeah, width increases. This is because the area under this curve is constant. You're going to see that soon, yeah? The area under this curve is constant. To keep the constant, if the width increases, if the spread increases, the height has to decrease, yeah? So that the total area under that is constant, yeah? So the probability is constant, yeah? So similarly, now, if I decrease sigma, if I lower the value of standard deviation, what will happen when standard deviation decreases? The spread decreases. And you can see that as the spread decreases, the height increases. This is to compensate for the area. Okay, now the height has increased because the area has to be constant. The height has increased and the width has decreased. So what I want to tell you here is the standard deviation helps us describe the spread of the data, while the mean helps us describe the position of the distribution. Yeah. Okay, now that you know the difference between the measures of location and measures of spread for a population, let's go back to the characteristics of a normal distribution. Okay. So the distribution of any particular data depends on mu and sigma. That's what we have seen now. Yeah, we have seen that it depends on the population mean and standard deviation. Okay, I'll come back to the notation soon. Just a minute. So for example, if I have a distribution, this is one example, then I have another distribution. Okay, I'll come back to the notation soon. Yeah, that's a notation, how you describe a normal distribution. And if I have a distribution like this, I have 3 different types of normal distribution here. Yeah, 3 different spreads. Each normal distribution has the same basic properties. Okay, the properties of these normal distribution, although they look different, they have the same basic properties. And what are these properties? We have seen some of these properties. Yeah, each distribution is symmetrical about its mean. The median and the mean are equal in each case because these are symmetrical data. So the median for this distribution will be equal to the mean because the data is symmetrically distributed. Similarly, the mean will be equal to its median because the distribution is symmetrical about the mean. The mean will be equal to its median because the data is symmetrical about the mean. Yeah. The distribution is bell-shaped. Each of these distributions are bell-shaped. So they all look different because they are for different data, but they have the same basic properties. They all are symmetrical about its mean. The median and mean are equal. The distribution is bell-shaped. And for each one of them, as you move away from the mean, the probability of finding or an event happening or is less likely to occur as you move away from the mean. Okay. If a variable x, if I have a variable x and I choose it randomly from this population, then I can say that any variable x, okay, any variable x, if I pick randomly from this population, I can say that a random variable x has a normal distribution with mean mu and sigma variance sigma square, and I can state the distribution or use the notation of this form to describe this distribution. And how am I going to read this? I will read it as x is a random variable that follows, x is a random variable that follows a normal distribution with a mean mu and a standard deviation sigma, or a variance sigma square. So that is how we state a normal distribution. So how am I going to read this? X is a random variable with a normal distribution. X is a random variable which follows a normal distribution with a mean mu and a variance sigma square. Okay. So mu and sigma are the parameters. We're talking about the population of the normal distribution. Okay. And that is why this is the way you denote the distribution. Okay, now another important thing. Before I go to that, let me ask you this question. Can you answer this? Good. Yes, that's right. So we're going to see the rule, how it's going to be distributed. So mu helps us decide the mean, population mean, to describe where the data is located, and sigma square helps us describe how the data is spread. Okay, so now the most important thing, area under all normal curve are same. That is, for all normal distribution, area under the curve is spread is same. Okay, area under the curve is same. The spread is same. That is, 68.2% of the data will occur in this area, and that is between plus sigma and minus sigma. That is between 1 standard deviation on either side of the mean. So 68.2% of the data occurs in this area between 1 standard deviation of the mean, and 13.6% of the data lie in this region on either side of the mean. So there are 13.6, 13.6, okay? And in the red region, 2.3% of the data will occur in this tail, in the red region, okay? Okay, and this rule is also called as empirical rule. It's got another name, I'll come to it. If the data has a normal distribution, 68.2% of the data lies within 1 standard deviation, we have seen that. And what percentage of data lies within 2 standard deviation? So it is 68.2 plus 13.6 plus 13.6. So it is around 95% of the data. Yeah, I can say that 95.4% of the data lies within plus or minus 2 standard deviation. So you have 68% within 1 standard deviation, 95% within 2 standard deviation, and within 3 standard deviation, plus or minus 3 standard deviation, you have around 99% of data. It's almost 99.7 or 100% of data. It is just, yeah, different books have different percentages there, yeah. So this is also sometimes called 68, 95, 99 rule, yeah. So it's the same empirical rule, okay. Anyway, so 4.6% of the data lies because 2.3% plus 2.3%. So 4.6% of the data lies in this red region. Okay. Now, using this understanding, we can compare entirely 2 different examples, like categories, like IQ level and cholesterol level. Yeah, they both are completely different examples, but the area under these 2 are equal. Okay, that is, here what is, you can say that if I pick a random variable x will follow a normal distribution with a mean 100 and variance sigma square. So 100 is your mean for this example, and sigma is equal to 15. Similarly, for this example, 5 is the mean and 0.5 is the sigma. Let me write it as sigma square so that you don't get confused. That means the mean is 100, so you write down 100, and then sigma square is 15 square, so sigma is 15. So 100 plus 15 is 115. 115 plus 15 is 130. 100 minus 15 is 85. 85 minus 70, 15 is 70. Similarly, here sigma is, because sigma is here 15, so you can add 15 each time. Here it is 0.5. So 5 plus 0.5 is 5.5. 5.5 plus 0.5 is 6. So 5.5 is 1 standard deviation above the mean. 6 is 2 standard deviation above the mean. 4.5 is 1 standard deviation below the mean. 4 is 2 standard deviation below the mean. Similarly, because sigma is 15, from here. That's your variance. It is sigma square. So 115, 100 plus 15 is 115. So 115 is 1 standard deviation above its mean. 130 is 2 standard deviation above its mean. Similarly, 85 is 1 standard deviation below its mean. 70 is 2 standard deviations below its mean. But the area under this is same. Yeah. So from our empirical rule, we can see that clearly that the area under the area in the shaded region for both are same. The area shown shaded for each of the distribution represents the same percentage of the total area under each normal curve. Because as you can see, this is 68.2. Yeah. So 50% of the data lie below the mean. So 50% of the data lie below the mean, below 100. And we know that 68.2 lies between the first standard deviation. So half of 68.2 is 34.1. So 34.1% of data lie between the mean and 115. So total 50 plus 34.1 is 84.1. Similarly, 50 plus 34.1 is 84.1. So the area under both normal distribution is going to be the same. Yeah, the mean is different, standard deviation is different, area is same. The probability of finding a random variable X will be the same in the shaded region. Okay. So now, what is the percentage of data in the interval X less than 150? If I ask you this question, you have to determine the probability of finding a random variable X, which is less than 115. Good, it's 84.1% because 50 plus 34.1. What is the probability of finding a random variable X less than 150? What is the percentage of data in the interval X greater than 5.5? So the now question is, the random variable is above 5.5. So somewhere in this region. So X could be anywhere in this region. So what is the probability of finding the random variable X in this region? Remember, the total probability under this area should be 100%. So what is the probability of finding 5.5 here? Good, 15.9. 100 minus 84.1, which is nothing but 15.9%. Okay. Now, what is the percentage of data in the interval X less than 25? Good, that's right. It's 50%, X less than 25, because the mean is 25. You can see from here, mean is 25 and sigma is 5. This implies sigma is 5 because sigma square is 5 square. So the next point will be 25 plus 5 is 30. Then you have 35. Similarly, on the other side, 25 minus 5 is 20, 15. Okay. So what percentage of data is in the interval X less than 25? So we are talking about this region. That is 50% of the data lies below the mean because this is the population mean, mu, yeah? Okay, next question. What percentage of data is in the interval X less than 86? Now, this gives you mu, and that gives you sigma is equal to 6. So what percentage of data lies below 86? Good. So here you have mean as 80 and because standard deviation is 6, 80 plus 6 is 86, and it's just asking you what percentage of data lies below 86. So that's right, 84.1. Good. Now try these two examples and enter the answer there. Good. Okay, so that's all for now. See you in part 2.